So if you have seen the slide from the first day from Wiki Middle talk, you might have recognized this thin blue line. Um, and imagine that if you see this on the planet outside solar system, how hard could it be to detect why we are in the time that detecting the terrestrial planet is still difficult, right? So my name is Priyanka Naraki. I just recently joined the Harvard team, and we are trying to study exoplanet atmosphere. And this is the project that we are proposing the instrument concept for the upcoming giant telescope. It's called FIOS, the literal interferometry-based instrument to search for oxygen in exoplanet atmosphere based on Benami et al. 2018. And so recent simulation from Lopez Morales 2019 suggests that if you want to detect molecular oxygen in exoplanet atmosphere of the Earth analog, you need a spectral resolution of 300 to 400,000 in order to do that. If you move to the next slide, please. So now we try to have the prototype going on in our lab and try to see whether this concept is going to work or not. We have the two echelon arms going on, and once we have multiple of them, we can fit those slots over there and try to sample the oxygen A band. And this is the prototype that we are now reaching 300 to 500,000 of the spectral resolution. So if you want to know more about this in detail, come to visit me at the slide poster number 36. Thank you.
Hi, my name is Miles Curry, and I'm a grad student at the University of Washington. And I'm interested in using ground-based high-resolution spectroscopy to tell the difference between an atmosphere with oxygen that's biological in origin and an atmosphere with oxygen abiotic in origin. And specifically, the abiotic oxygen production mechanism that I'm interested in is water photolysis in the upper atmosphere. So I have this little cartoon down here, and this shows a planet with nitrogen and water in its atmosphere, and the dashed white line represents the water cold trap, and it effectively keeps water in the lower atmosphere. Next slide, please. And if you take away some of the nitrogen in the atmosphere, this causes the cold trap to rise in altitude into the upper atmosphere, and it also provides a way for water to get into the upper atmosphere as well. So once this water's in the upper atmosphere, it can get photolized, and the hydrogens will escape to space because they're relatively light, and the oxygen will stay in the upper atmosphere because it's relatively heavy. So we're working on a method that uses ground-based high-resolution spectroscopy to tell the difference between this type of spectra and a spectrum with biological oxygen. So please come to my poster to learn how we're doing this. Thank you.
Hi, I'm Samantha Gilbert. I'm a grad student at the University of Washington, and I'm studying interpreting biosignatures with future instruments. So in searching for life on other worlds, it's theorized that the smoking gun we're looking for is the simultaneous detection of methane and oxygen. And the rate at which these molecules are created at the surface can actually give us clues as to whether they come from life or not. So what this means is we probably really need to quantify surface flux in order to correctly identify evidence of life with confidence. So there are a lot of instruments that are going to be trying to detect biosignatures on exoplanets, and these instruments are going to be optimized for different observing techniques in different wavelength regimes. And these wavelength regimes in turn determine which molecular features these instruments can hope to detect. However, there are some challenges, of course. These instruments can't directly detect surface flux. Instead, we actually have to infer them indirectly from chemical abundance. Also, in the mid-IR, ozone has to be used as a proxy for oxygen. However, as you can see in this plot from Jim Casting, there are potentially 3 different orders of magnitude of oxygen that can give you the same ozone column depth. And of course, there are other challenges as well. Next slide, please. So in order to prepare a community for facing these sorts of retrieval challenges, we really want to compare different observing techniques in order to simulate how we may interpret signs of life using these instruments in the future. So this is work in progress, and so far we've used a photochemical and a 1D climate model to generate simulated spectra. We'll use instrument simulators and try to retrieve chemical abundances from the noisy spectra, and then we'll try to back out surface flux from these chemical abundances, and then try to determine if these fluxes are in fact biological or abiotic in origin. So if you want to hear more about interpreting signs of life using future instruments, please come visit me at poster number 16. Thank you.
Hi everyone, good morning. Milton Mendonça from Federal University of Rio Grande do Sul State in southern Brazil. That makes me an oddball here, as well as being an ecologist and not an astronomer, or even a normal biologist, let's say. But I'm doing a sabbatical in the UCLA. I wouldn't miss this thing with Carl Sagan's name on it. And I like astrobiology a lot. It's my second career. So I'm trying to bridge things here, and I think ecological theory has a lot to contribute to astrobiology. And, we need to make a proper effort about that. One of my first ideas when I started looking at the astrobiology literature was that lithopanspermia, which is being increasingly used as an example of things that could happen. Captain Hand even mentioned it briefly in his talk before. If you show that to an ecologist, he would say, well, this is dispersal. This is something going from one place to the other and then back. And that gave us an idea, gave me an idea that we could have a kind of a metabiosphere, which is sort of like a metapopulation. We have populations linked through dispersal. That there's a lot of interesting things to this population which are not quite isolated. So my question here is, when and where could this metabiosphere occur? One of the first questions would be, perhaps during the late heavy bombardment, we would have more chances of this occurring. There's been a suggestion of life coming from Mars to the Earth, actually not the other way around. Perhaps these periods of high impact frequency, like you find on mass extinction on Earth, could be the other way around, could be mass seeding of life to other planets too. And next slide. Of course, you have systems like TRAPPIST-1 in which you can probably have more planets in close together, in which this is much more likely to happen than probably our solar system. So thank you very much, and have a look at the poster later if you want.
Hi everyone, I'm Shanna. I'm also an oddball. I'm on the math side, so I'm studying like arithmetic, geometry, and gradient side theories and math and physics. Hopefully finishing my PhD in the University of Bonn and studying my HGS. So I went a bit meta here, and we're trying to look at the actual effect of CPT symmetry violation from cosmic neutrinos on enzymatics, matter distribution, molecular reassembly, and the cool supersymmetric counterpart of the neutrino is the neutralino. It also turns out to be a Majorana fermion, which means it's an antiparticle. So we think that sort of self-anti is really important in the topic of immersion. So if we categorize like emergence as quantum computational complexity, then we think that is the sort of gauge invariant thing that's growing in a thermodynamic equilibrium. So we try to get this categorical equivalence between like the algebra, whatever category the gauge is, and the QPU. And then through commutativity, you can get this sort of computational complexity and get a multi-space-time algebra. Okay, so if you, Neil Turek, Perimeter Institute, kind of put out this theorem about it is possible that the CPT symmetry is actually conserved if you have a mirror universe actually equal and opposite on the other side, whatever that means. So you can use the beautiful language of mirror symmetry by Maxim Komsovich and get this cool correspondence between the superconformal field theory, which you can get to be an algebra. So it's all like algebraic, but it's arithmetic algebraic. We can also play with blockchain and AI, merge those together using geometric algebra to screen for false positives. So there's something weirdly private about the sort of about emergence and the compartmentalization, which Paul talked about yesterday. So what is the role of GC symmetry in massive gravity, where you have a non-zero mass of the graviton on geocycles, and then all of this should describe emergence. So if you want to play with like the geometro biodynamic of Majorana, read on. I'm here. Thank you.
Hello everyone, I'm Domenico. I'm finishing up my PhD at the Observatory of Turin in northern Italy, and I'm here to introduce you to a new planet me and my colleagues in GAPS team have discovered around star BD minus 114672, or as I call it, BD blah blah blah. And thank you. I really was really hoping for that. And the planet we found orbits this star, in which there was already a giant planet on outer orbits. And this planet is at 74 days in period, and it's Uranus mass-sized planet, so it's not really your typical habitable planet. However, next slide, please. What we notice is that our new planet orbits very closely to the inner boundary of the conservative, mind you, conservative habitable zone for this star. So I was curious about it, and I wondered, could there be any additional planets within the habitable zone? After all, most of super Earth systems show that they come in closely packed configuration. So why not? I was curious, and basically what I did was injecting different planets with different masses within the habitable zone to see whether for a variety of eccentricity for a new planet, they would be ejected or impacted with the inner planet, or they would be completely stable to perform a future observation on this system. So that was it, and I still have time. That's wonderful. Never happened to me before. So if you are curious about it and you want to see me rambling on with this stuff, come see me at poster number 2. Is facing the back side of the room. Thank you.
Hi, my name is Per Dwarf, and I'm a PhD student at Stockholm University, and I'm studying the multiplicity of substellar binaries and brown dwarfs, which are these objects that are more massive than planets, but not quite as massive as a star, so they can't really ignite hydrogen. And when you look at a random star in the sky, you might realize that it's probably or most likely part of a multiple system that is unresolved. It's a very bold claim to say that 3 out of 2 stars are in binary systems, but for the most massive stars, this might actually be true. However, as you go down in primary mass, the multiplicity frequency goes down. And we typically use multiplicity to infer formation mechanisms. So this is quite important for the formation of giant planets, as brown dwarfs and giant planets have many things in common. Furthermore, once we've discovered a binary system or a multiple system, we can monitor them, and we can, if we monitor them for a long time, we can constrain their dynamical masses from their orbit. And if we also can assess their ages, we can obtain pretty good benchmarks for calibrating evolutionary models. However, at the very lowest substellar masses, just few tenths of the Jupiter masses, the statistics is very low. We don't have that many systems that have been discovered. Luckily, we just recently discovered 3 of them, seen here. And what's also further pretty interesting is that each of these images is actually a collapsed data cube. So each pixel contains a spectrum of more than 2,000 wavelength elements. And yeah, that's pretty much all I wanted to say. And if you wanted to hear more about brown dwarfs and so on, then you can see me at poster number 4 this afternoon. Thank you.
Hi, I'm Akash Gupta, second-year graduate student at UCLA with Jackman. So recent observations have told us that there is a lack of planets around 1.5 to 2 Earth radii, as shown on this plot, which shows relative occurrence changing with planet size. Now, typically, this radius valley is understood as a result of photoevaporation, but something that we have been able to demonstrate, and also Ginsburg et al. 2018, that this radius valley can also result as because of atmospheric mass loss due to luminosity of the planet itself. The source of the luminosity being the planet's primordial energy of formation. And we can also explain a multitude of observations through this mechanism. As an example, what I have here is how the 1D distribution of planets changes and how the planet distribution changes as a function of planet size and orbital period. And what you can clearly see is that the observations are our results are in good agreement with the observation. So in a nutshell, the Coulomb mass loss mechanism can explain the radius value as a byproduct of planet formation process itself. And not just, it doesn't simply explain the radius distribution of planets or its variation with orbital periods, but it can also explain the variations with stellar mass, metallicity, age, and insulation flux. And so if you would like to know more about these results and our work, please come and visit me at poster number 20 or just catch me anytime. Thank you.
Hi, I'm Megan Mansfield. I'm a grad student at University of Chicago, where I work with Jacob Bean and Edwin Kite. And my poster is a kind of whirlwind summary of 4 papers that we've recently submitted that came out of this collaboration that was focused on finding the best ways to look for atmospheres on terrestrial planets orbiting M dwarfs. So the first 2 papers present some new modeling results. One is new 1D modeling that includes self-consistent TP profiles for these planets and also the effect of a solid surface on their spectra. And then the second uses some GCMs for these planets to develop a scaling that relates the atmospheric pressure to the amount of heat redistribution that you would get. Next slide, please. And then we use these 2 new models in the other 2 papers, which present ways to use eclipse photometry to detect these atmospheres. The basic idea here is if you saw a cooler atmosphere than what you would expect to see on the day side of these tidally locked planets, then that could be due to one of 2 things. Either a thick atmosphere that's redistributing heat to the night side, or a high albedo, thinner atmosphere that is high albedo because it's hosting clouds. But either way, you would be able to infer the presence of an atmosphere. And we found that using eclipse photometry, you could detect atmospheres around these planets with as little as 1 secondary eclipse with James Webb. A caveat on this is not a method that you would use to detect atmospheres on habitable planets. This is going to work for slightly hotter planets that are easier to see in secondary eclipse. But it can still teach you a lot of interesting stuff about how the XUV flux from M dwarfs impacts the atmospheres of the terrestrial planets orbiting them. So if you have any questions about this, come talk to me or check out my poster. Thanks.
All right, hi everybody. My name is Jackman. I'm a graduate student at Vanderbilt University, and I'm here to talk to you about microlensing. So we've heard a lot over the past couple of days about the types of icy worlds that might be habitable and the type of life that could exist on them, but we haven't heard so far yet how we might find those. Microlensing is an exoplanet detection method that you might not have heard much about, but can actually help us discover these new planets. And there are ways that you can get involved today. So first off, there are several resources available that have public data for you to get your hands dirty, essentially, working with. The first, all of these data are located on the NASA Exoplanet Archive, which is hosted here at Caltech. And there are 3 main data sources that you can choose from. We have microlensing observations in astrophysics, or NOAA. And this is a 14-year several years, high cadence microlensing survey towards the Galactic Center. We have some data from the Korea Microlensing Telescope Network, KMT-net, that's available as well. And finally, we have a whole bunch of data available from the United Kingdom Infrared Telescope, or UCIRT, which has data from 2015 all the way to 2018 now. We're taking 2019 as we speak. This is infrared data located on the archive. And this is the project I primarily work with. Next slide, please. So these public codes that I listed here, and also on my poster, the little QR codes that can take you directly to the GitHub, are ways that you can actually look at our data and then say, okay, this is how we're going to fit a microlensing light curve. A lot of them are built on Python, so they're pretty accessible to most folks. And the reason that we want you to get involved is because of the upcoming mission W1. A huge portion of this telescope is going to be focused on microlensing, but we have a serious person power problem, and we want to invite you to get involved before this telescope launches.
Hi, I'm Helen Parrish from UCLA. I'm primarily focused on general circulation models of planetary atmospheres within the solar system, but of course, exoplanets involve a lot of Venus analogs, and so the simulations I did could very well be relevant to exoplanets. And I've focused on a lot of the interesting features you observe in Venus's atmosphere. Venus has a lot of characteristics that are, for example, not like Earth's atmosphere. There's a lot of difference in morphology at different altitudes and as seen in different wavelengths, which you know, we might look at exoplanets in different wavelengths in the future. These show some of the interesting features. The largest gravity wave in the solar system occurs on Venus's atmosphere. That was recently discovered. And there are also very irregular, variable dark features, which some people have suggested could be possibly associated with some kind of microscopic life. So there is the potential for astrobiology on Venus, even though it's not traditionally considered an astrobiology target. Next slide, please. Obviously I'm observing a lot of complex features here related to wave structures. And right now, that's not the thing we can see on exoplanets, but maybe in the future, looking at the phase curves of exoplanets in detail. In this particular study, I've looked at different types of waves which are known to be formed on Venus. These are the largest scale waves, which are Rossby and Kelvin waves, and compared with observational data to validate them. So if you're interested in the potential of Venus as a type of exoplanet, please come and see me at my poster.
Morning all, my name is James Jackman. I'm a third-year PhD student at the University of Warwick in the United Kingdom. And my poster is on how we're using NGTS to find the biggest flares from the smallest stars. So stellar flares, for those of you that aren't aware, are explosive phenomena that occur in the magnetic field of a star when magnetic field lines reconnect. They emit intense amounts of energy, in particular for exoplanet habitability, in the UV and in X-rays. They're also could be associated with coronal mass ejections, so the combination of high-energy XUV irradiation and charged particles could cause ozone depletion and atmospheric loss. But on the other hand, for planets around M stars, the UV flux might be useful for prebiotic chemistry, get various pathways going. So we're using NGTS to observe stellar flares across a large range of spectral types and see how various properties vary. So properties such as duration, amplitude, and energy. So an example plot on the right-hand side, of which you can see an updated version on my poster, shows the maximum flare energy varying as a function of spectral type. And we can see for M stars, you can have hundreds to 1,000 times the Carrington event, which is the maximum energy we've ever seen from the sun. So the updated data you'll see on the poster, number 26, stretches from stars similar to the sun all the way down to the brown dwarf boundary with a spectral type of L2.5. If we go to the next slide, this flare here, which is the first flare ever detected from an L2.5 star, making it the coolest star, both literally and figuratively, to ever show a white light flare to date. So come to poster 26 to learn about how we're finding stellar flares in NGTS and how that can be used to improve our knowledge of exoplanet habitability. Thank you.
Hey everyone, I'm Simon Locke. I'm a postdoc here at Caltech. So if you were to think of a planet, you would probably think of something that was roughly spherical, rotating as a solid body, and sort of have a density of a few grams per cc. However, I wanted to tell you that there are planetary objects out there that look nothing like that. And these are sort of a group of planetary objects called Synestias. So giant impacts, collisions between planet-sized bodies, are the most catastrophic events suffered by planets during their accretion. And normally, for low energy impacts, what you end up with is something like here on the left. You end up with a co-rotating planet surrounded by a Keplerian disk, shown here as a function of angular velocity, with some messiness in between, which we don't want to talk about. But if you have a higher energy impact, and it helps also if you have higher angular momentum, what you end up with is a post-impact body that is tens of percent of the mantle is either vapor or supercritical fluid. And what happens is the planet expands to the point that it sort of spills out into its disk. And you form something that is sort of a continuous, both thermodynamic and dynamical structure that looks, sort of is one continuous silicate gas giant, effectively. And we name these Synestias, or if it helps, the Daily Mail carefully seems to term them mega space donuts, as you can kind of get the impression from the Scientific American article. So why do you care? There's likely not going to be life swimming around in a silica vapor atmosphere, but actually these are very important objects because they change how the body starts. So for example, your planet actually ends up raining out of your atmosphere rather than your atmosphere degassing from your planet. But also they provide a very different mechanism for moon formation. Next slide. So instead of forming your moon in a vacuum by spreading the disk, you actually end up forming a moon inside the vapor of the Synestium. You sort of cook it, which gives it a very different composition. And this works very well for explaining the composition of our moon and could have implications for what elements are available in exomoons. Thank you.
Hi, I'm Daniel Yahalomi. I'm a postdoc at the CFA working with Dave Latham and the rest of the test science team at Harvard and MIT. Today, actually, I'm a little bit off topic. I'm going to talk about a self-lensing binary system in Kepler, KOI 3278. So the system is a white dwarf and that orbits a G-star. And it's called a self-lensing system because as the white dwarf passes in front of the G-star, it gravitationally lenses the light. When it passes behind, you get a white dwarf occultation that mimics a transit signal. So in 2014, this was the first self-lensing system that was discovered by Ethan Kruse and Eric Agel. At the time, they only had Kepler photometry, so they created an Einsteinian gravitational model of the system. Since then, we have 16 spectral observations from trace and high-res. This allowed us to get a spectroscopic estimate of the G-star stellar parameters, effect, temperature, metallicity, surface gravity. We use that to redo the Einsteinian model, as you can see on the left. The spectra also obviously gave us radial velocities, which we then used to create an independent model of the system. So we now have two independent models, both modeling the same system, one with Einsteinian gravity, one with Newtonian. Next slide, please. And what we found, not surprisingly, is they both predicted similar estimates for the white dwarf mass, about 5%, within about 5%. What we then were able to do is create a joint model using photometry and the radial velocities and Einsteinian Newtonian gravity, which allowed us to remove a lot of assumptions about the white dwarf and get a model-independent test of the mass-radius relationship for white dwarfs, that you can see here. If you want to talk about this system specifically, self-lensing binaries in general, or tests, come find me, poster 42. Thanks.
Okay, I'll make sure you're just 1 minute away from your lunch. So I'm Coco Zhang from University of Michigan. So I study chemistry in protoplanetary disks, which is the birth environment for planets during the first 10 million years. So my goal is to understand what physical and chemical process sets the initial composition for planets. So for the poster, I focus on carbon monoxide, which is one of the simplest molecules. And for many years, people think it just carries the interstellar medium abundance to the disk, and they keep it there for 10 million years. But now we are finding it's more complicated than that. So the abundance actually changes dramatically, order of magnitude variation from the inner disk to the outer disk, and it also changes with the evolutional stage. So if you want to know more about the initial composition for planet formation, please come to my poster number 44, which is the long fibrous one close to the entrance. Thank you.
Let's thank all of our speakers one more time. And we have announcements before you leave.